In the next 20-25 minutes, I will try to present some of the current ongoing effort to develop to port CP2K on CPU. And as a background, I'm common matter theoretical physicist, so I'm not quantum chemist, and I'm not really a solid state physics researcher, or was not really solid state physics researcher. So DFT for me is, I know the method, but I don't know all the full details. So I apologize in advance if I miss some point from the DFT point of view. So I'm currently at ETH Zurich and working more specifically at the Supercomputing Center, Swiss National Supercomputing Center in Lugano. So I'm not doing research, and I'm not using this software for research purposes. We are only developing it from a technical standpoint. And this is important to keep this in mind, because we have a different view about how things can be ported and might be ported. So first of all, we have to identify what are the main operations that are used in CP2K. And as some people already mentioned, as the two previous speakers already mentioned, CP2K is, they didn't really mention it, but they guessed what CP2K is. CP2K is a DFT code that uses a mix between Gaussian and plane wave basis set for modeling DFT. And it has been particularly tailored to work well for protein, molecule, gas, and liquid or atomic structure. So what if you benchmark, if you profile CP2K, what you will find is that the most demanding part are diagonalization, calculation of potential force and energies, computation of the density through what we call collocation method, and a bit less with parallel FFTs. A word about the method that we used, that we try to use to port CP2K on GPU. The first thing is that we try to port all the effort we do, at least at CSCS, is to try to provide external libraries that are vendor agnostic. And in order to do that, we use a more extensive we use the concept of separation of concern, as the library can have its own development cycle. Each of the library we develop or we work on try to implement only a small subset of all of the needed functions that CP2K needs to have implemented or ported to GPU. And one of the reasons we do that is that it's in general easier to validate the code change and to add support for new hardware or even new vendor. The second method of development is to take a subpart of CP2K and develop a dedicated library for it, and make it vendor agnostic if possible. The problem with this solution is that it's usually tightly integrated into the code, and if someone wants to reuse this part, this module in another context, it will probably have quite a hard time to do it. One of the things that we discover is that doing that we need to do a proper planning for these parts for developing dedicated libraries. And usually, if we think that you need 3 months to do this work, just multiply by 2 or 3, and then you are probably in the right amount of time you really need to port this part of the code. Another aspect that I also discover working on CP2K is that documented code is actually important for the other developer to work on, to maintain and work on. I will not go into great many detail about separation of concept of concern, but basically you have the definition of Wikipedia definitions, which is in two single sentences. In computer science, separation of concept is design principle for separating a computer program into distinct sections. A program that embodies this concept is often called a modular program. The basic idea behind it is that a program shouldn't be a big blob of code and should be split into small modules that you can work ideally independently, that you can work on independently one from the other. I know everyone knows in the audience that it's not always possible, but it's a good way to actually be able to port code on GPU or other accelerated platform. The other advantage of this type of methods or concept is that these small functional blocks can be made available to other projects as well. And I think this is an important aspect of this. So the first effort to port CP2K on GPU was through the use of DBCSR, which stands for Distributed Block Compressed Sparse Raw Matrix Library. Sorry, it's long name. The library tried to solve a small subset of problem, which is mainly doing distributed sparse matrix multiplication. And this problem happens very often, is one of the main aspect of CP2K, because potential and density coefficients are stored in a very sparse matrix with very small block size. And if you want to do DGEM using this kind of matrices, you cannot really use a conventional matrix multiplication like BLAS, like DGEM implemented by BLAS. So on the top of it, these matrices are often distributed over multiple MPI ranks, so you have to find a way to do that. And DBCSR took two slightly different approach. The first one on CPU, because it was the original code. They make extensive use of batching and library design for small DGEM. I cite two of them, which I know. libxSMM, which is developed mostly by Intel, but work as well on AMD and other platforms, and libSMM, which was, I don't remember who developed the library. It doesn't really matter. And the second approach was to use GPU. And in that case, there are two different types of porting. The first one is to use template programming to generate kernel codes at runtime. And of course, when you use templates, C++ templates, often the kernel code that is generated is very highly GPU dependent. So you have a lot of machinery behind that you need to run for each new GPU that is coming on the market. The second approach is to use OpenCL, and it's more generic approach, and more importantly, it does not require auto-tuning methods, which means that it will work relatively efficiently on any GPU, Intel or AMD or NVIDIA. The second library that was included almost 4 years ago is the Sirius library. CP2K does not natively support DFT method in the plane wave domain, and this was a request from many users, CP2K user. How can we include DFT? How can we include DFT method in the plane wave domain? And at CSCS, we have been developing a library that just does this. So The library is called Sirius. It has native support of MPI, OpenMP, Cuda, and IP, and it is also part of exciting code and big DFT codes. The only functionality of Sirius is to compute the ground state, force, and stress, and we try to do it as efficiently as possible. From a design point of view, we started the development with the idea that it should run on GPU and not only on CPU. So it's designed from the ground up for running on GPU. And as I said, it is integrated in CP2K, but it's also integrated in Quantum Espresso, which means that we had for quite a long time Quantum Espresso couldn't run on GPU, but with the use of Sirius, they could do many calculations on GPU. And the last thing I want to say is that combined with CP2K methods, you can consider this solution. So Sirius on the top of CP2K on the top of Sirius. Sorry. You can consider this solution as a good alternative to Quantum Espresso. So this is a graph that is showing a comparison between, in that case, Quantum Espresso Sirius and the Quantum Espresso porting Cuda fortran. But we can reproduce the same type of simulation with CP2K, and we would get pretty much the same numbers. So as you can say, both codes now support GPU, but the problem with the current version of Quantum Espresso is that it only supports CUDA hardware, while Sirius is far more generic, which means that you can run the same simulation on AMD GPU or NVIDIA GPU, and hopefully on Intel GPU when they will be available on the market. The third piece of work that we did was to try to replace SCALAPACK PDGEM, which is actually a real bottleneck in CP2K, especially for RPA calculation. And for that, we developed a library that is called COSMA, which try to minimize the amount of communication between between MPI ranks, and try to maximize the size of local DGEM that you run either on GPU or CPU. The last aspect of it was we didn't want to reshuffle all CP2K code, so we tried to minimize the amount of CP2K code we had to modify. And to do that, we developed an interface that just replace the PDGEM, so the PDGEM call by the equivalent of COSMA call. The graph that you see at the bottom of the figure shows some of the results between different implementation of PDGEM. So SCALAPACK from MKL, COSMA on CPU, and COSMA on GPU. Those have been run on PINS date, which is Intel-based processor with P100 GPU. So it's a Cray system. And already the efforts that we made trying to minimize the amount of communication is already paying off on for the CPU only run. So if you compare only the CPU run, you already get a factor 2 difference in performance. Now, if you offload all DGEM on GPU, then you improve the performance by a factor 3. Now, if we include that in CP2K and do some real simulation, you will get actually a much better improvement, performance improvement. So for that, we use 64 H2O molecule in a box, which is a conventional benchmark for regression that we use in CP2K. And we run those benchmark on V100. So the nodes are dual socket Intel Broadwell with 8 V100 GPU. So I think it's a crazy storm system. But for those simulations, we only use one socket. And on the table, you can see the total runtime and the fraction that is spent in PDGEM. And just running COSMA, offloading PDGEM to COSMA, we get a factor 60 improvements in the PDGEM fraction and around a factor 50 improvement in factor 10 improvement in total runtime, which is non-negligible. The other thing is that if you run the same simulation on, you can run the same simulation on AMD GPU, and what you would get are results that are very similar to V100. Now, if you are limited, if you don't have GPU, just changing to just using an external library like COSMA and running the same simulation on CPU, you will get a factor 3 improvement. So we did that on the Cray-Shasta platform, which is composed of EPIC CPU. So the point here is that by just replacing one call by an external library, we reduce the amount of time we spend in PDGEM. So in other words, PDGEM is not a major bottleneck in many CP2K simulation anymore. Something that I didn't really discuss yet is that CP2K, like many other DFT code, is often dominated by matrix multiplication. And in CP2K, we have actually quite a few different matrix size and shapes, which means that we can have small matrix multiplication, quite a lot of those, or very large matrix multiplication. And solving this problem in a generic way is actually difficult. In general, small matrix multiplication are faster to run on CPU because these operations are memory bound and often too small to fully utilize accelerator large GPU. On the other hand, GPU, if you have very large GPU, then very large DGEM, sorry, then running them on GPU is actually more efficient than running them on CPU. So to solve this conundrum, we split somehow the matrix multiplication depending on their size. Small DGEM are handled by libxSMM or libSMM. Medium DGEM through BLAS, and large to very large DGEM, we try to offload those to GPU. This functionality has been implemented in Cuda, but unfortunately it's vendor locked. And since we are working on multiple different architecture, we had to find a solution. We had to find a more generic solution for it. And this is where SPLA enters. Sorry. SPLA was initially developed for another purpose, which is doing distributed matrix multiplication with layers that are more specific to DFT codes. And it is different from SCALAPACK or COSMA in that regard. The other goal of the library was to provide a generic interface to NVIDIA and AMD GPU. And the anecdote is that although the library was not initially thought to do a matrix multiplication offloading on GPU, it actually adds this functionality from day one. So the advantage of as I said, the advantage of this implementation is that the library can be used without any knowledge of Cuda or IP. And of course, if the matrix multiplication, if the parameters of the matrix multiplication are too small, then BLAST will be used internally. So it's very a drop-in replacement of the DGEM of the matrix multiplication offloading that NVIDIA implemented in Cuda. I think a graph would probably give a bit more interesting results. So the graph that you see is really a PZ gem on PIDS dates, and we compare the different implementation of this function and run them on the cluster. And as you can see, depending on where the data are, either host memory or device memory, SPLA is always dominates the two other implementation. Even COSMA, which is developed with the idea of minimizing MPI communication. And if you look at a specific implementation of provided by Craig is always at the bottom. Now, if you use SPLA in CP2K, then the first thing that we could observe is that specific calculation like MP2 calculation can gain a factor 4 in factor 4 improvement. Other part of CP2K can also benefit from it, and most of the time it's really replacing DGEM call with offload DGEM. An idea, something that is actually similar to what NVIDIA has done with BLAST. Finally, there are two other type of operation, and this two equation will be the only one you will see in this talk. So the first one is to compute the density. So either through the use of plane waves, through the use of wave function, or in that case, we compute the density coefficient and we multiply them by the appropriate Gaussian, by the appropriate Gaussian. And you have a discrete sum of them, and you have to evaluate this sum for each point of the real space grid. The second operation is a more conventional one, which is computing the coefficient of potentials, for instance, in the basis set you are working on. They are actually mathematically they are identical once you discretize the integral. In practice, implementation is slightly different. So to port this calculation on GPU, we use a different method than the one we use on CPU. So if you want to do that on CPU, we realize that we can recast this problem in using DGEM. And the issue is that those DGEMs are relatively small, so they are usually memory bound. The second approach was to just apply brute force. By evaluating exponential and polynomial on each grid points, and then do the summation. Now, if you want to port that on AMD or NVIDIA GPU, actually the code are almost identical. Then the brute force method is actually far more efficient, because the issue we have with this type of calculation is that you cannot is that the grid parameters and the number of coefficients you need and so on and so forth is not constant. So you have to deal with all those things. But porting, so now if you compare GPU with CPU, we can get a factor 10 improvement. And one important aspect of this is that all implementation scale linearly with MPI and OpenMP, because we use these two paradigms for CPU, or with the number of GPU for GPU port. So CP2K is a very large code, so it's more than 1 million line of code, and it's actually a major undertaking to run CP2K on both NVIDIA and AMD GPU. This was made possible because of the use of external library and modularization of the code. There are a few aspects that made the porting difficult. The code is made, the algorithms are not well documented. So very often you have to do a little bit of reverse engineering to understand what are the mathematical operation you have to do, and or to understand what the code is doing in practice. The third thing that we learned is that many parts of CP2K just do the same thing all the time, and somehow you have code duplication that appears, and that's why I wrote "Do not reinvent the wheel." So to minimize this, we try to use library as much as possible because benefit can be very large. I cited COSMA, SPLA, etc. And this is particularly important because it saves both development time and improve flexibility. The last one, which is not as important as people may think, but I think you shouldn't be afraid to use a different language to implement a specific feature, especially if it can save development time. But this is a minor point. The last slide is give you a list of links to the different library. Of course, a link to CP2K that many of you know, COSMA, SPLA, and Sirius and DBCSR. And I would like to thank many of our partners for support, either financial, technical, or scientific. And the list is really incomplete, but I hope it covers most of the contribution. Thank you very much.
Thank you, Matthieu. Is there any question? Let's see. Otherwise, I have one. Well, I start to ask a question, and maybe someone raised the virtual hand, and then I can ask. So I've been following the work around Sirius for quite some time. This is very interesting and fascinating approach. And I understand the need of, kind of vendor agnostic, high-level domain-specific type of interface to port part of the code to accelerator in general, not just in VGP, to accelerate in general. My question is a little bit about low-level. Obviously, you implement this high-level API, that has a very sophisticated, for example, matrix multiplication that is aware about the data distribution, et cetera, et cetera. But ultimately, inside that code, you will need to use, like some library, some BLAS. So at the moment, based on your assessment, based on where you've been able to run CP2K with these libraries, what's the current state of the art about the maturity of libraries, the low-level numerical libraries, in your opinion, on NVIDIA GPU, but also on other platforms?
So, as I say, we don't try to reinvent the wheel. So most of the library I've been mentioning are based either on cuBLAS, eBLAS, BLAS and LAPACK, or even SCALAPACK for some aspects. So the most basic operation, which is often the matrix-matrix multiplication, is not, we use external library for that, and we use vendor libraries. The good aspect, because we don't have the resources to develop this library first, and second, I don't think we can beat NVIDIA, Intel, or AMD at just implementing those very low-level functionality. So there is no point for us to spend time on this low-level library. But what we have done is, for some of them, try to provide a bit more generic way of thinking, because if you have to think about, okay, no, I have to run on AMD GPU, but I have a code that is ported on NVIDIA. How can I, that is using NVIDIA hardware. So how can I do that? The first thing would be, okay, are we using NVIDIA libraries like Cuda? If yes, then effort for porting on other hardware is actually minimized, because very often the other vendor will have similar functionality in other libraries. So it's really modifying small piece of code within the library. Then in Sirius, what we did is exactly that. We have, of course, some high-level way of doing DGEM, but it's mostly for practical purposes. But in the end, when you look at the call trees, you will find that it's always calling either BLAS or QBLAS or EBLAS or ROCBLAS. So I think that's probably answer your question, or at least partly answer your question.
Yeah. And for everything that is not covered by this library, because there's always some piece of code that is not covered
Yes.
by this library, what approach are you, what's your preference in that case?
Okay, my preference is to go back at the math and try to recast the problem into a matrix-matrix multiplication problem. Because very often you will find that many methods, after some digging, many methods can be mapped to DGEM, to matrix-matrix multiplication. And if you do that, you have actually, it's a big step towards more generic programming. I gave an example, for instance, during my talk, where actually this method does not work very well, but it's a very specific operation. This is its collocation integration routines that we had to develop specifically for GPU, because the matrix-matrix multiplication approach didn't work well in that context. But very often what we try to do is to reduce the problem to a set of linear algebra operation in general. And if you do that, you benefit a lot from using using optimized library like MKL or whatever.